Okay, moment of inertia, second moment of inertia, part 2. So in this video I'm going to continue talking about second moment of inertia, alright, and some advanced topics related to that. Alright, so let me open the screen. Alright. Alright, so okay. So we already talked about definition of second moment of inertia and using method of integration to find moment of inertia about an axis, and it will be arbitrary axis by integration. So, and I talked about polar moment of inertia in the previous video. So now I'm gonna define something for you guys, is radius of gyration. So radius of gyration, or as French say, gyration. Alright, so this is how we define it. If you have an area like this, like x-axis, and you guys learned already that moment of inertia about x-axis could be defined by this integral. So if you consider dA to y is dx, right? While evaluating this integral, y squared y times dA, we can find that, right? But let's imagine just that we can put this area like a narrow rectangle, right, above your x-axis, and let's say that distance that I put it, I call it Rx, right? So consider that like a narrow rectangle that has same area, this arbitrary shape, and it has distance Rx, right? And I want to see if it's possible to find an Rx that gives us same area, same moment of inertia about x-axis, right? So for this narrow rectangle, a moment of inertia about x-axis, since everything is like same distance as equal to Rx, right? It's Rx from x-axis. Moment of inertia for this narrow rectangle is going to be basically whatever that area is times Rx, right? That distance Rx squared, right? Okay, so remember these two guys, let's say they have same area. You know, by setting this equal to original moment of inertia for this arbitrary shape, you see that I'm going to be able to find that distance Rx that's going to give me same moment of inertia about x-axis, right? So let's now relook at this again. So I started with this arbitrary shape, right? So what I'm saying here is that it's possible to put this area, you know, make it like in the form of a narrow rectangle which has distance Rx from the x-axis, so that such that, you know, this moment of inertia of these two are the same. So these two are actually equivalent, right? So then that distance that we find, we are going to call it radius of gyration, right? So this is like radius of gyration. So we're gonna call it Rx because it's about x-axis, right? So any area, arbitrary area you look at, right, it's possible to find that distance Rx such that when you put that area like in the form of a narrow rectangle, these two moment of inertia of these two shapes are the same. Okay, so the larger the moment of inertia, the Rx is going to be larger, obviously, right? The largest. So moment of inertia was a measure how distributed this shape is about the x-axis. It was a measure for that. For example, if you look at, for instance, this case versus this case, moment of inertia here, let's say the areas are identical. Moment of inertia here is bigger than here because it's like farther, right? Let's look at this case. This case, moment of inertia, let's say areas, all these cases, areas are the same. Moment of inertia, this case is going to be less than this one. So if this is I1, I2, I3, then you see I2 is going to be greater than I1, I3 is going to be smaller than both, right? Okay, so the moment of inertia by itself was a measure for distribution of the area about the axis, whatever axis x. But radius of gyration is similar, does similar thing, right? If you put that in the form of a narrow rectangle and set the moment of inertia as identical, then that distance we have for for that narrow rectangle, in order to maintain same moment of inertia, that Rx, we call it radius of gyration, and that's gonna have, you know, the larger that is, the farther distributed your area is. Alright, so it's very easy. This is the definition. So what you guys have to do is, if you want to find the Rx, this is how you guys do it. Divide Ix by A, and then radical of that is going to give you Rx itself. So we can define radius of gyration in y direction like this. You can do for polar moment of inertia, you can do this similarly. And by the way, let's look at the units. You know, moment of inertia, the unit for that is going to be what? Length squared times area. So whatever the unit for length you have is going to be here like that. Length to the 4. So if you have millimeter, it's going to be millimeter to the 4. If you have inches, inches to the 4. Okay, so how about radius of gyration? You saw that I said this is like a you know, it's like a distance. So it's going to be length, whatever length you have, millimeter or inch. So here you see that this is length to the 4, length to 2. They cancel, you have length squared, and then a square root of that is going to give you length. Alright, so this is just definition of radius of gyration. When we study buckling, you're going to see in 309, when we study mechanics of material, topic of buckling, we're going to see radius of gyration there. Okay, next thing I'm going to talk about is parallel axis theory. Parallel axis okay. Again, this is completely mathematical, geometrical, you know, discussion here. So let's see what that is, parallel axis theory. Okay, so let's say I have an area like this, right, and then I have the centroid of it located here, and then let's say I have x-axis passing this centroid, you know, in a horizontal axis, and let's call that axis actually x prime, right? So, and let's assume that I have moment of inertia about this axis. I call it x prime, ix prime. So this is like ix prime, let's say it's given, and I want to find, here's my problem, I want to find I moment of inertia about x-axis, which is parallel to x prime and has distance of, let's say, d. The distance between these two axes is like d. I want to see if I can find a relationship between ix prime, which is moment of inertia about x prime, and then ix. This is my goal here. So let me repeat again. I assume that x prime is like an axis passing the centroid of the cross section, right? And then x-axis is another axis, is not passing the centroid, is parallel to x prime, and I know that it has distance d from x prime axis. I want to see if ix and ix prime are related to each other or not. Alright, so how do I do that? To do that, let's see this. I'm going to define a coordinate system here, x prime, y prime, and then I'm going to define another coordinate system, x and y. And then let's say this one, the origin is O prime, this is this is O and this is O prime. And by definition, what is ix prime? What is ix prime? Ix prime is technically, if you have differential, let me consider it here. If you have differential element here, dA, and I know that its distance from x prime axis is y prime, technically ix prime is y prime squared dA, right? If you evaluate this integral for this entire region, that's going to give you ix prime. So how about ix? Ix by definition is this. So the distance from this for so what matters is the distance from this differential element to x-axis here. So if I call it y, right? So by definition, ix is y squared dA. All right. So let's see what else we can say. Ix is now, what is y? Y is, if you look at here, y is basically is y prime plus d, right? Y prime plus d squared. And then dA. Alright, so this is the integral I need to evaluate. Okay, but I can expand this. So if I expand it, let's see, y prime squared plus 2y prime d plus d squared dA. And then, what else? Okay, so I can break this integral into three pieces. So I have y prime squared dA plus integration of 2y prime d dA plus d squared dA. Alright, this is what I got. So let me move to another page. Alright, so this is what I got. Alright, so what is the first term here? Actually, literally that first term, that guy, is ix prime. And then let me look at this guy. This d squared is constant, comes out, and the integration of dA will be just a, so d squared times a. And then let's look at this guy. This guy 2d is constant. I'm gonna take it out and I'm gonna get this, right? Okay, so let's see what this is. Now if you look at this integral, this is basically first moment of area, right? About the x prime axis. Now that thing at the beginning, when I started this discussion, I said that x prime is passing the centroid C. That was the key thing I mentioned there. if x prime is passing the centroid, this integral actually is gonna be 0, because first moment of area about axis passing the centroid must be 0, right? So why is that? Because, you know, if you look at, you know, the formula we had for finding the centroid was this. If you consider dA like that, the location of centroid, let's say it's here, was what? The formula was this: y tilde dA divided by area. So if this x prime axis is passing the centroid, so if the centroid is here, then means what? Y bar must be 0, right? The distance, if this x prime axis is passing the centroid, it means that the y coordinate of the centroid must be 0. So in other words, here, if you look at here, the integral, this integral that I have here must be 0. So this is significant, what we found. So what we found is this. This is what I found. Okay, let me restate that. I have centroid here. I have found, let's say, I know what moment of inertia is about x prime axis. And then if I want to know what moment of inertia is about x axis, which has distance of d, right? There's like a d distance between x axis and x prime axis, right? If I have that d, then what this equation tells me is this: you don't need to evaluate that integral. You know, the integral was what? Y squared dA. You don't need to reevaluate this integral about x-axis again. All you need is, since I will have ix prime, you just add to that another term, area times the distance between these two axes squared. That is why this is called parallel axis theorem, because, you know, it just is about parallel axes. But one thing you guys have to be careful is this: the fact that ix prime must be about an axis passing the centroid. So be careful. We cannot have just two arbitrary axes and then write this relationship there. You know, one of them, ix prime, must be about you know, axis passing the centroid. Alright, so what happens if, you know, we can do the same actually for, this. You know, let's say point C is the centroid, right? So let's say I have y prime axis is passing the centroid 2, right? And then I have another axis here, y. So this is all prime. So let's call this distance between x-axis and x prime dy, and I call between y-axis and y prime axis, I call that dx. So guys, you know, if you are interested in, I can write same thing for iy. If I want to find iy, I can say iy is basically iy prime plus this time area times this distance, which is dx. So this one is dy, this one is dx. dy, if I name this one dy, this one dx, right? So this is what I can say. Alright, so now similar, proof is similar, right? So if you look at these two equations, let's add them up. Let's add them up, the both sides, and see what I get. On the left side, I'm going to get what? Ix plus Iy. Right? On the right side, I'm going to get Ix prime plus Iy prime plus A, let me write it here, A times dx squared plus dy squared. Alright, so what is Ix plus Iy? I exploit y is polar moment of inertia about O axis. And then this guy is polar moment of inertia about O prime axis. And then plus area times dx squared plus dy. So what is dx squared plus dy squared? If you look at here in this right triangle, if I build a right triangle here, right? So this is dx, this is dy. This distance is like O prime. Dx squared plus dy squared will be O prime, right? And let's call that O prime RO, right? There's like R O, like a distance between those two guys. So if I call this RO, then you write this relationship: JO equals JO prime plus A times RO squared. Right? So similar to what we had for this guys, right? But distance is measured from point to point. So for polar moment of inertia, again, if you have polar moment of inertia about centroid, any other point you want to find polar moment of inertia, all you need is what? To add polar moment of inertia for about the centroid plus area times the distance between this new point and the old point. Alright? So this is parallax theorem. So this is gonna help us to actually find this rule we just found. This this theorem I just proved that to you is gonna help us to find moment of inertia for composite shapes, complex shapes, without taking integral. So let me open the notes and show you something there. See what I'm talking about. Alright, go here and then go here. Okay. I don't see. Okay. My resolution is too big. That's why I don't see the course material. Let me see how I can figure out. Oh, okay. Must be here, not course documents, course weekly content. Go here, moment of inertia. So let's see how this is helping us. Okay, so these are what I talked about in lecture 1, lecture 2. So, with what I just said, we can, for composite areas, we can develop like a flow chart to find moment of inertia for composite shapes. This is similar to the approach that you learned to find centroid for composite shapes. For composite shapes, in a lot of times in engineering, we are working with very common areas, but the common popular areas like rectangles, circles, half circles, or and then we mix them to each other and we make composite shapes. So, for example, as an example, I'm gonna look at this problem. So, look at here. We have like an I-beam, which is like it's not symmetric. You see, it has one axis of symmetry, vertical one, but so here, if you want to find moment of inertia of this, we have 3 rectangles. I'm going to show you next that how we can do that, how we can actually find moment of inertia for shapes like this. Alright, so to do that, we are gonna do this. So these are like the steps. Let me read that for you, and then I'm gonna perform it, follow that for that example I showed you. So for composite shapes, this is what we gotta do. At first, we divide the given area into its simple shape parts, like common parts we are familiar with, like circles, as I said, like rectangle, right, square, or half circle. Then we have to locate the centroid of each segment and find the perpendicular distance from each centroid to the desired reference axis that I'm interested in finding moment of inertia about. Alright, and then calculate moment of inertia for each segment using parallel axis theorem. And then finally find total moment of inertia by adding all algebraic summation of all those individual moments. If you have a hole in your composite shape, that will be like you have to subtract moment of inertia of it from the total, right? If it is solid, it will be added. So let's look at this guy. This guy, okay, let me show it on the notes on the dot camera. Let's go here, let me open it. There you go. So I'm gonna redraw that guy here, and let's do it. See what if I can drag this guy down. Alrighty. So we have this I-beam now. Let me put dimensions. Okay, dimensions are as follows. You have here one plane of symmetry, axial symmetry is like that, right? Here is 12 millimeter. Here is 12 millimeter. This is 6 millimeter. This is 8 millimeter. This is what, 24. This is 6 millimeter. This is 24 millimeter. 24 millimeter here too. Alright, so we have all dimensions, right? So what you're interested in, so if I call this y-axis, it says what is moment of inertia about x-axis, if this is like my x-axis. We want to see what's the moment of inertia of this guy about x-axis. Alright, so the way I'm gonna do this, I'm gonna break this guy into pieces. So obviously here we have what? We have it says what is Ix, right? So how do I find it? I can break it into pieces like this. So this one piece, another rectangle like this, so piece 1, piece 2, piece 3. Alright, so then piece by piece we have to find polar, not moment of inertia, and then add them up, right? So segment 1, segment 2, segment 3, right? Here I'm gonna write Ix about their centroid. Each section is gonna have moment of inertia about its centroid, and then I'm gonna write here that distance between their centroid and this x-axis. So if I call it dy, and then I'm gonna find here Ix about, using parallel axis, about x-axis, and then at the end I'm gonna add them up, right? Okay, so let's look at our segment 1. Segment 1 is this guy. Is a rectangle, and if you consider its centroid is located here, right? So what is the distance between its centroid and x-axis? Is this distance, right? You have 24 plus another 3, 27. For segment 2, The centroid is at the center, so we are lucky for that guy. X-axis is passing its centroid, so distance for that is going to be 0. And then the third segment is having distance similarly 27 from x-axis. So 3 millimeter here, 24 here, 27. Okay. So for this segment, if your head axis x prime, you define x prime axis passing its centroid parallel to x, then moment of inertia for that was going to be equal to what? My base is 24. My height is 6 divided by 12, right? So 24, 6 cubed divided by 12, right? And then for second one, base is what? Is 8. Height is 48 divided by 12. For the last one, this piece, if you had your x-axis going, x prime axis passing its centroid parallel to x, moment of inertia was going to be 48 6 cubed divided by 12. Okay, so these are moment of inertia about for each segment about their centroid, right? Axis passing their centroid and parallel to x. To find Ix but x-axis, we have to, if there is di, dy, you have to square this, multiply it by their area, and then add them to each other to find the Ix. Maybe it was a good idea for me to have like a column for area, right? So area for this guy, segment 1, is 6 times 24. For this one is 8 times 48. And then for this one is gonna be 48 times 6. Alright, so these are the areas. So Ix, let me write it here. And not much room here, but Ix for segment 1 is what? Is this guy. 24 6 cubed divided by 12 plus the area is 6 times 24 times 27 squared. So for segment 1, you're going to have that moment of inertia entire thing is 105 408 millimeter to the 4. Okay, for segment 2, this middle one is what? Is basically 848 cubed divided by 12. That one is going to be 73728. And then for segment 3, this guy is going to be equal to this 48 6 cubed divided by 12 plus 27 is the distance, must be squared, times the area of that, which is 6 times 48. If you calculate this, you're going to find Ix3 equal to 210 816 millimeter to the 4. So here is millimeter to the 4. Alright, so the total Ix for the entire shape, entire thing, about the x-axis is going to be these three numbers added. So total is going to be 389 952 millimeter to the 4. Alright, so this is my moment of inertia. So what if I'm interested in finding radius of gyration about x-axis too? As I said earlier, Rx is basically what? Ix divided by area and then square root of that. So what is Ix? I found it 389,952. What is area? Is 24 times 6 plus 8 times 48 plus 6 times 48. This is the total area. So if you do that, you're going to find 21.9 millimeter. So this means what? Moment of inertia of this guy is equal to moment of inertia of a narrow rectangle with the same area, this area, with this distance, 21.9 millimeter from x-axis. These two guys, this and this, they have same moment of inertia about the x-axis. This is what radius of gyration is. Alright, so that's about it. You know, we covered moment of inertia, the topic. So you guys see that parallel axis theorem, it can help us to find moment of inertia for composite shapes. And right, you don't need to evaluate the integrals here. You learned about the method of integration, so let me open actually the notes and show you there. So we learned about method of integration, right? Method of integration, you build like differential elements and integrate. And you learned about polar moment of inertia, radius of gyration, and parallel axis theorem, which was the main topic of this lecture. So I proved that to you, and I showed you guys how you can use it actually to find moment of inertia for composite shapes like this without taking the integral. You don't need to reevaluate the integral. That your book has your book or other books, reference books, they have for common shapes, they have moment of inertia as listed in a table, and there are like manufacturers also, you know, if you look at their catalogs, they may have, let me show that actually doesn't hurt. Taking a look at that. Yeah, right, let's see. If you look at your book, at the end there are like for common shape, popular shapes like this one, for example, like an I-beam. You know, polar moment of moment of inertia with x-axis is given, radius of gyration Rx is given. For y-axis, you see x-axis and y-axis. Iy is given, radius of gyration Ry is given. So, and this is like commercial cross sections you may see in the market. And let me see. Yes, let me see if they had also another table. Okay, for like common shapes, like centroid and moment of inertia for common shapes like this, like a half circle, quarter circle. This is like the location of centroid, this is the area, and then moments of inertia are in this table. Let me see if I can zoom it. So it's at the end of your book. For rectangle, I proved that to you guys, that on x prime is going to be bs cubed divided by 12. Let me zoom it more. So can I go up? Yeah, I showed that to you guys. Ix prime is bh cubed divided by 12. For the base, 4 times of that, and then for j, polar moment of inertia, C is basically adding those two. for a triangle. I didn't show it to you guys, but proof is not difficult. But we can use these, you know, as long as they are listed in the table, we can use that. And for circle, I showed that half circle and quarter circle, ellipse, right? Common shapes. And these are like common shapes, and I showed you guys the commercial catalogs, you know, selected see rolled steel shapes may see in the market. Your book has like you know, if you look at manufacturer catalogs, they have large variety, large list of tables. This. Alright, so the parallel access theorem is a strong tool to help us to look at composite shapes. Sometimes you may put a commercial cross section next to two of them, you know, weld them to each other and make a beam. So in other videos that I'm gonna post, I've done some problems related to moment of inertia using integration and also using like method of that we use for composite shapes, and watching them is very useful. So I encourage you guys watch them. Alright. So I hope you find this useful.